Hi, I am Sanjay Patel. In this video, we are going to solve some interesting problems based on all the things whatever we have discussed in our first 11 videos or first 11 lectures. So let us start with the first simple example. If R plus dot is a commutative ring, then prove that a plus b whole square is equal to a square plus 2ab plus b square for all a and b belongs to R. Okay. This result is true not only for a plus b whole square, it is true for any power of this binomial. So a plus b raised to n, we can write that binomial expansion in a commutative ring in which a into b is equal to b into a. So it is very simple. Say we start like this. A and b are any two elements, and consider a plus b square. The meaning of a plus b square in a ring is a plus b into a plus b. This we can write using the distributive law. I can multiply this with each of this element. So a into a plus b into a plus b. You can fix this x and this as x and use the right distributive law. So this is we are writing by the distributive property. Again, by the left distributive law, this we can further expand and write as a into a plus a into b plus b into a plus b into b. And this is nothing but a square, and ab plus ba, as the ring is commutative, this and this element both are same. So ab is equal to ba. So I can write 2 times ab, okay, and plus b into b is b square, because a into b is equal to b into a. So it is proved. So thus a plus b whole square is equal to a square plus 2ab plus b square for all a and b belongs to R is proved. A very, very trivial example. What I want to discuss here is the converse of this problem is also true. But before that, let me give you this important remark, and that you can prove yourself. If R plus dot is a commutative ring, then prove that, or let me write directly, if R plus dot is a commutative ring, then we have this a plus b raised to n is equal to, say, nc0 a raised to n plus nc1 a raised to n minus 1 into b. So we can use that binomial expansion and write this way. So ncn and b raised to n. This is true for every n belongs to n. So this is an interesting and easy exercise for you. You can use a mathematical induction to prove this. What I am interested in this problem, we have shown in this problem that if R is commutative, then a plus b whole square is equal to a square plus 2ab plus b square holds. Is the converse true? Means if in a ring R, if this formula holds, if this identity holds for every AB belongs to R, then can we say R is commutative? And the answer is yes. So that I want to show you as our next problem. Let R plus dot be a ring, and suppose A plus B whole square is equal to A square plus 2AB plus B square. This is true for every A and B belongs to R. Then prove that R is commutative ring. R is commutative ring. So let us see how to do this. To prove a ring is commutative, we must show that A into B is equal to B into A for any two elements A and B. So let us start with AB belongs to R, be arbitrary. And we want to show that AB is equal to BA. So I start with this given hypothesis. So therefore, I can write A plus B whole square is equal to A square plus 2AB plus B square. This implies I can write this as A plus B into A plus B is equal to A square plus 2AB plus B square. Okay. This we can simplify as we have written in the previous problem as A into A, that is A square, plus A into B, then plus B into A. Here I cannot write 2AB because I don't know the ring R is, means I want to prove actually the ring R is commutative. So plus B square is equal to A square plus 2AB plus B square. Okay. And by cancellation law, because it is a operation of addition and ring R is a group with respect to addition, so I can cancel the elements from left and right. Okay. What I will get is AB plus BA is equal to say 2 times AB. So this will be left. Okay. Now you know the meaning of 2AB is AB plus AB. 2x in the ring means x plus x. So I can write this as AB plus AB. And by using the cancellation law, I can cancel this AB and write this as BA is equal to A into B. Okay. And what is A and B? They are arbitrary elements. So what is proved? BA is equal to A into B for all A and B belongs to the ring R. And that means the ring R is commutative. Ring R is commutative ring. Okay. Fine. Now let us go to the next problem. Say number 3. We have defined characteristic also. Just recall what is the meaning of characteristic. A characteristic of a ring R is n if n is the smallest positive integer such that n times a equal to 0 for all a belongs to R. So let me give you one interesting and nice example. Let R plus dot be a commutative ring, with characteristic 3, with characteristic of R is equal to 3. Okay, then show that A plus B whole cube is equal to A cube plus B cube for all A and B belongs to the ring R. Okay, so let us understand this. Here, characteristic of the ring is 3. That means that 3 is the smallest positive integer such that 3 into x equal to 0 element for every x belongs to R. Remember, 3 is the smallest positive integer satisfying this condition. What I want is only this, that 3 times x is equal to 0 for all the elements in the ring. Now, since R is commutative ring, we can write say a plus b whole cube using that binomial expansion, and we know the expansion of a plus b whole cube, that is a cube plus 3a square b plus 3ab square plus b cube. Okay, this is true for every a and b belongs to ring R. We are using the binomial expansion in the ring, in the commutative ring. Okay, now this means here in the right hand side, this is a square into b and this is a into b square. So this you can treat as some element of the ring. So you can call it x, and 3 times some element of the ring is always 0. So this gives us a cube plus 0 plus 0 plus b cube because of result number 1. Okay. So a and b are elements of the ring. So a square into b also belongs to R. And for any element x belongs to the ring R, we have 3 times x is equal to 0. So I can write 0 in place of these two terms. And that proves the result. So we have a plus b whole cube is equal to a cube plus b cube for every ab belongs to R. Okay. Now the interesting thing is to see whether this holds if I take a plus b raised to 4. So let us discuss something about this question. Can I say if characteristic of ring is 4 and R is commutative ring, obviously let us take commutative, then can we have a plus b raised to 4 is equal to a raised to 4 plus b raised to 4? Then answer is no, it is not always true. Okay. You know what is the binomial expansion of a plus b whole raised to 4? We can use that Pascal's triangle, or we can write directly also if you know the expansion of a plus b whole raised to 4. A plus b raised to 4 is a raised to 4 plus 4 times say a cube into b plus 6 times a square into b square plus 4 times a into b cube plus b raised to 4. This is the expansion. You know how to write this using the Pascal's triangle that you have done in your school. We can use this Pascal's triangle 1 1 1 2 1 1 3 3 1 1 4 6 4 1. This gives the expansion of a plus b raised to 1. This gives the expansion, the coefficients of the binomial expansion a plus b square. This gives me the coefficients of the binomial expansion. So all these things you know very well. So I am writing using the binomial expansion. Since R is commutative, we can do this. And since the characteristic of the ring in this question is 4, it means 4 times x is equal to 0 for every x belongs to the ring. Let me write over here. Because of characteristic of R is 4, we have 4x is equal to 0 for every x belongs to R. So this term and this term will be 0, but we cannot say about this term. Okay, this term need not be 0. So this term will remain, and therefore I cannot say that a plus b raised to 4 is equal to a raised to 4 plus b raised to 4. Let me write properly. So we cannot conclude that a plus b raised to 4 is equal to a raised to 4 plus b raised to 4. So this is not equal. Okay. But if you take a plus b raised to, say, if you take characteristic of r is equal to 5, then again we can write the same result as the previous one. Okay. But if characteristic of ring R is 5, okay, then we can write a plus b raised to 5 is equal to a raised to 5 plus b raised to 5. Because I can prove immediately here, the expansion of a plus b raised to 5, if you are interested, you can write like this, a raised to 5. Just use this to write the next step. This will be, say, 5, 10, 10, 5 and 1, and 1 is also here. So I can write this expansion as 5 times a raised to 4b plus 10 times a cube into b square plus 10 times a square into b cube plus 5 times say a into b raised to 4 and finally say b raised to 5. And since characteristic of this ring is 5, then the characteristic of the ring is 5, we have 5 into x is equal to 0. So this is 5 into x. This also you can write as 5 into 2 into a cube into b square. So this is also 5 into x. So this is 0, this will be 0. By same arguments, this is 0 and this is also 0. So finally we get a plus b raised to 5 is equal to a raised to 5 plus b raised to 5. So from this set of problems, what we are observing here is if we have a plus b, characteristic of the ring R is 3 or 5, the result holds that a plus b raised to n is equal to a raised to n plus b raised to n. In fact, the result is true in more general form if the characteristic of the ring is a prime number. So let us state that interesting problem. The next problem is, I think it is, yes, the next problem is number 4. Let R be a commutative ring with characteristic of R is equal to small p, where small p is a prime number. Okay. Then prove that, this is an interesting and important example, prove that a plus b raised to p is equal to a raised to p plus b raised to p for all a and b belongs to R. So this will be very useful later on also. So an important problem, and let us understand the solution of this. Since R is commutative ring, we can write a plus b raised to p is equal to a raised to p. Okay, pc is 0, that is 1. Then pc1 a raised to p minus 1 into b plus pc2 a raised to p minus 2 into b square and so on. Let me write some general term also. Say PCR and a raised to p minus r into b raised to r plus and so on, plus the last but one term is pc p minus 1, then a into b raised to r minus 1, and finally we have b raised to, this is not r, this is a into b raised to p minus 1, and finally in the last step you will get b raised to p. This is true for all a and b belongs to R. Let us call this as result number 1. Okay. In a commutative ring, we can write down the binomial expansion for say, any integer n, any positive integer n. So I have written this thing. Now let us use the fact that characteristic of R is P. Now characteristic of the ring R is small p, and that means p times x is equal to 0, 0 element for every x belongs to the ring R. So this is another thing. Okay. In order to prove the result that a plus b raised to p is equal to a raised to p plus b raised to p, I must show that all the terms in this binomial expansion except the first and the last term, all other terms must be 0. So what I need to prove is these all are of the form p into something, or in other words, these binomial coefficients are say divisible by p, and that is a known fact. Okay, so let me just write in detail. We know that PCR means the formula for NCR. PCR is equal to p factorial upon r factorial into p minus r factorial. Okay, and I am interested only in this binomial coefficients PC1, PC2, PCR and up to PC minus 1. So I am putting a restriction here that 1 is less than or equal to r less than or equal to say p minus 1. Just I am considering these values. Okay, then for 1 less than or equal to r less than or equal to p minus 1, no, let me not write here. Okay, we know this binomial, this formula for PCR. This I can write as p factorial is equal to r factorial into p minus r factorial into PCR. Okay, into PCR. Let us call this as number 3. Now we know that p is prime number. Okay, and p factorial contains the factor p. It is 1, 2, 3 up to p. So we have p divides p factorial. Okay, that is p divides the left hand side of result 3. P divides p factorial. So p divides the right hand side also, right hand side of the result 3. Okay, so p divides this integer. It is something like a into b into c. This is one integer, another integer, and this is a third integer. So p divides a into b into c, but p is prime. Okay, so I can say that either p divides r factorial or p divides p minus r factorial or p divides PCR. So that means p divides r factorial or p divides p minus r factorial or p divides PCR. You know this result from the number theory. If p is prime, okay, and p divides a into b, then either p divides a or p divides b. So I am using this result in a generalized form. Not only for two integers, it is true for any number of integers. Say if p divides a1, a2, a3 up to an, I can say that p divides at least one integer out of this a1, a2, a3, an, and that is valid only when p is prime. Okay, it's a very famous result from number theory. So p must divide one of this integer, but for 1 less than or equal to r less than or equal to p minus 1, okay, if the value of r is between 1 to p minus 1, we have p does not divide, say, r factorial. We can say p does not divide r factorial, and also p does not divide p minus r factorial, which is also less than p minus 1. P minus r factorial is also less than p minus 1, because these are all integers which are, say, less than p. R is less than p, so p cannot divide any of this by the same type of arguments. This is a known fact. So only possibility is p divides PCR is proved. This is proved for 1 less than or equal to r less than or equal to p minus 1. If p divides PCR, that means PCR is equal to p into something. So let us call that something to be, say, p into some integer, say p into m, for some integer m belongs to, say, n. Okay, fine. So this is true for all the numbers for every r between 1 to p minus 1. So that suggests that if you take a general term in this result, binomial expansion, this p divides this PCR. So PCR is a multiple of say p. Okay, so from result 1, I can say, therefore, in result 1, we can write, say, PCR into a raised to, it was p minus r into b raised to r, as p into m into a raised to p minus r into b raised to r. Okay, and this is some element of the ring. This is some element of the ring. So we have p times something, p into something. Let us call this as x. So we have p into x, and therefore this must be 0, because the characteristic of the ring R is p. So p into any element of the ring is 0. So that suggests that all the terms in this binomial expansion for 1 less than r less than p minus 1, all the terms here are 0, which are underlined. So I can write directly a plus b raised to p is equal to a raised to p and b raised to p. Only this first and the last term will left. So therefore, and remember, so therefore from 1 we have a plus b raised to p is equal to a raised to p plus b raised to p. So this problem is also solved. Let us go to the next one. Example number 5. Let us consider that very important ring Zn, which we have not proved in detail. So I will be now mentioning that very important result. Say, consider the ring Zp, plus p, dot p, okay, of residue classes modulo p. We know that Zp is a commutative ring with unity. Okay, so the problem is, what I am interested here is prove that Zp is an integral domain. Zp is an integral domain if and only if p is a prime number. and only if P is prime number. So that this is very, very important result. Okay. Let us solve this. We know that this ZP comma plus P comma dot P is a commutative ring with the unity element, And what is ZP? Elements of the ring ZP, you know very well that ZP is nothing but the set of all residue classes modulo P, and it has exactly P elements. So class 0, class 1, class 2, and I can write up to class P minus 1. So these are the elements of this ring. Now I'm interested in establishing this result that this ZP becomes an integral domain if and only if the number P is a prime number. So there are two parts here. In the first part, let us start this way. In the first part, we are given that ZP is an integral domain. You know what is an integral domain? It is a commutative ring with unity without any zero divisors. And we want to prove that P is a prime number. P is prime number. This I will be proving by the contradiction. So suppose P is not prime. Suppose if possible, P is not prime. Okay. That means P is a composite number. So I can write P is equal to A into B as a product of two integers. Let us assume that A and B are positive integers. And I can write that 1 is less than A is less than P, and 1 is less than B is less than P. So the number P, if it is not prime, has two factors A and B, which are different from 1 and different from P. Okay. Now if these two integers are same, what we can write is the equivalence class of this integer is same as equivalence class of A into B. Okay. But what is equivalence class of P? It is 0. So I can write equivalence class of A into B is equal to equivalence class of 0 or class of 0, because we know P is congruent to 0 mod P. We understood what is the meaning of the residue classes here. This I can write as class A dot P class B is equal to class 0. And this class A and class B are elements of the ring ZP. Class A and class B belongs to ZP, and we are given that ZP is an integral domain. So it has no zero divisors. So whenever we have x into y equal to 0, so this is x, this is y. So x into y equal to 0 element means at least one of this element must be 0. So therefore we must have either class A equal to 0 or class B equal to 0, because in an integral domain, if x into y is 0, then x is 0 or y is 0 must be true. Okay. And if class A is equal to 0, means this class A is equal to 0 means A is, by definition, A is congruent to say 0 mod P. Okay. Or I can say that B is congruent to 0 mod P. Okay. And that means either P divides A or P divides B. And that gives me the contradiction, because P divides A means P is less than or equal to A, or P is less than or equal to B. Okay. Okay. So this is a contradiction, because we are we have written here that A is less than P and B is strictly less than P. So I can say a contradiction to, this is a contradiction to A is less than P and B is less than P. Okay. So therefore our supposition must be wrong. Our supposition must be wrong. What was our supposition? That P is not a prime. Hence, we have proved that P must be prime. P must be prime number. Now, let us discuss the converse part. In the converse, what is given is the number P is prime, and we want to show that ZP is an integral domain. We know that ZP is a commutative ring with unity. That is already written in the beginning. The ZP, plus P, dot P is a commutative ring with unity. So here it is remaining only to show that ZP has no zero divisors in order to prove that ZP is an integral domain. So it only remains to show that ZP has no zero divisors. No zero divisors. Okay. So let us take two elements in ZP. Let class A and class B belongs to the ring ZP. And suppose the product of these two elements, class A dot class B, is equal to the zero element. That means class A multiplication modulo P class B is equal to the equivalence class of 0. This is the zero element in ZP, and zero element is nothing but class 0. This we can write as class A into B, and this is equal to class 0 by definition of multiplication modulo P. And if two equivalence classes are same, we know that these two integers are congruent modulo P. So this is congruent mod P, because we know that this result, say class X is equal to class Y, okay, then X is congruent to Y mod P in this relation. When we have defined ZP, we have discussed all such things, and this means P divides A into B. P divides A into B. Okay, P divides AB minus 0 means P divides AB. And since P is prime, I can say that either P divides A or P divides B, because P is prime number. And if P divides A, I can say A is congruent to 0 mod P, and P divides B means B is congruent to 0 mod P. Okay. And if A is congruent to 0 mod P, means if A and 0 are related to each other by this relation, I can say that class A is equal to class 0, or here this means class B is equal to class 0. See, from where I have started? I have started with A dot B equal to 0 and have proved that either A is 0 or B is 0. So thus we have proved that A dot B equal to 0 implies A equal to 0 or B equal to 0. Remember, this is 0 element of the ring. So we can write like this. And this means the ZP has no zero divisors. No zero divisors. And therefore, the conclusion is Zp comma plus p comma dot p, this ring is an integral domain, because we are already having that it is a commutative ring with unity. So in this problem, we have proved an important result, that the ring Zp of residue classes modulo p is an integral domain if and only if p is a prime number. And as an immediate consequence of this result is that you can also state that Zp is a field if and only if p is prime number. So let me write down that as the next problem. So problem number 6. The last problem I am taking here is say prove that the ring Zp comma plus p comma dot p is a field if and only if p is a prime number. P is a prime number. Okay. See, this is very, very simple, and I will not write in detail, just show you the main steps. There are again two parts. In this part, suppose Zp is a field. Suppose Zp is a field, and we know that every field is an integral domain, that we already proved. So I can say that Zp is an integral domain also, because every field is integral domain. And if Zp is integral domain, then by the above example, I can say that p is prime. So one way it is obvious. Conversely, suppose p is a prime number. Suppose p is prime number. Okay, and if p is prime, then we have proved in the above result that Zp comma plus p comma dot p is an integral domain. Is an integral domain. Also, we know that Zp has only p elements, exactly p elements. So that means Zp is a finite set, or rather a finite integral domain. And we have put a theorem that every finite integral domain is always a field, and hence Zp is a field. So let me write, but every finite integral domain is always a field, So Zp is a field. Remember, this is subject to the fact that p is prime. So thus, another interesting problem, that remember Zp is a field if and only if p is a prime number. Okay. And the last part of this my today's discussion of all these interesting problems, I want to introduce a small thing and discuss some problem based on this notation. The definition of nilpotent element of a ring. So consider, let R plus dot be a ring and A is an element of the ring R. Okay. If there exists some natural number n such that A raised to n is equal to the zero element of the ring, then A is called, or A is said to be a nilpotent element of the ring R. Nilpotent element of the ring R. So this is definition of nilpotent element. Okay, n is called degree of nilpotence. If such a small n, smallest n which exists, then The smallest value of n is called degree of nilpotence. Okay, just to understand this, let us take a simple example. Say, let us consider the ring R of say 2 cross 2 matrices with real entries. Okay, with the ring of matrices. This is the ring of matrices, and I want to explain that what are one example of a nilpotent element. So let us take a matrix A, so given by -1, say 1, 1. Okay, this is an element of the ring R. Then if I find A square, that is A into A, and that means -1, -1, 1, 1. Again -1, -1, 1, 1. And we know how to multiply two matrices. So first we consider this and we multiply with this column, first row with the first column. Let me take this. Yes, this column is to be multiplied with this row is to be multiplied with this column. So we'll get -1 into -1, that is +1. -1 into 1 is -1. Then again this row is to be multiplied with the second column to write the second element. So -1 into -1 is +1, and this -1 into +1 is -1. Now for the second row of this product matrix, we consider the second row of the first and we multiply with each of this column. So 1 into -1 is -1, 1 into 1 is +1. Again 1 into -1 is -1, and 1 into 1 is +1. So all this gives us 0, 0, 0, 0. That means the zero element of the ring. So what I have proved is A square is equal to 0. So A square is equal to 0. That is, A is a nilpotent element. Nilpotent element of the ring R. Okay. Likewise, you can give many examples of nilpotent elements. I want to just state one or two problems about nilpotent elements, and then you can try at home. I will just prove one or two examples. Let us see how much we can do. This is problem number 6. Now I will go to the next problem, number 7. Okay. If A is a nilpotent element, let me write this way. If A not equal to 0, a non-zero element, A not equal to 0 is a nilpotent element, in a ring, in a ring R, then prove that A is a zero divisor. So an interesting problem. A is a zero divisor. Okay. So in the ring R, we have A as a nilpotent element. Since A is nilpotent element, okay, there exists some positive integer such that A raised to that positive integer is equal to 0. So there exists some n belongs to n such that A raised to n equal to 0. Okay. What I want to do is choose m. Okay. Choose m be the smallest positive integer. Smallest positive integer such that A raised to m equal to 0. So that A raised to m is equal to 0. This is possible by well ordering principle. By well ordering principle, you can choose such a smallest positive integer m. See, nilpotent definition says there must exist at least one n such that a raised to n equal to 0, then a is called nilpotent element. So there can be many values of n, and out of all these values of n, we can choose the smallest one, and that smallest one we can call, say, m. Okay. Now this m is the smallest positive integer, but this m cannot be 1. Why? Because if m is equal to 1, then a raised to 1 equal to 0, that gives us a equal to 0, which is not true. We are given that a is not equal to 0. Okay, so I can say therefore this m is greater than 1, because if m is equal to 1, then we have a equal to 0, a contradiction. This is not true. So m is greater than 1 and m is a positive integer, means m is greater than or equal to 2. So minimum value of m is, say, 2. So therefore I can write this a raised to m equal to 0 as a into a raised to m minus 1 equal to 0. Okay, remember m minus 1 cannot be 0 because the minimum value of m is say 2. Or I can write this also as a raised to m minus 1 into a. That suggests that this a into something is equal to 0, and this a is a raised to m minus 1 cannot be 0, as, let me write this way, as a raised to, no, m is the smallest positive integer such that, let me write this as star so that I can write directly. Okay, from star we can say that a raised to m minus 1 cannot be 0. This will be better. From star, a raised to m minus 1 is not equal to 0, because m is the smallest positive integer for which a raised to m equal to 0 is true. So for m minus 1 we cannot have a raised to m minus 1 equal to 0. So we have found a non-zero element, okay, a raised to m minus 1, so that a into this equal to 0. A is also not 0. So thus a is not equal to 0 and a raised to m minus 1 is not equal to 0. But a into a raised to m minus 1 equal to 0 and a raised to m minus 1 into a is also equal to 0. So this, both the numbers a and a raised to m minus 1 are 0 divisors. In particular, I can say that a is a 0 divisor. A is a 0 divisor. Okay. So we'll see about this nilpotent element. There are some more interesting problems you can practice from the book. So thank you and have a good day.